everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBC CPS IISc. It's my pleasure to introduce today's speaker, Dr. Hariprasad Manjunath. He'll be speaking on multi-community spectral clustering for geometric graphs. Dr. Hariprasad Manjunath is an assistant professor at the School of Mathematics and Natural Sciences, Chanakya University, Bangalore. He received his PhD in Computational and Data Science from the Indian Institute of Science in 2022. Where his research focused on fast algorithms for eigenvalues of periodic matrices. His research interests include spectral graph theory, matrix analysis, numerical linear algebra, and geometric random graphs. He has previously served as postdoctoral researcher at INRIA, France, and as an assistant professor at IIIT Dharwad. Over to you, Professor.
Thank you very much. Thank you for giving me the opportunity. So I'll be talking about community recovery in random geometric graphs. So this is a brief outline. I'll introduce the background literature in random geometric graphs and with a brief about community recovery, and then we look at adjacency limiting spectra of soft geometric block model. So it's a random geometric graph model. So we use spectral method for recovering the communities in geometric graphs. So in spectral method, first we look at the eigenvalues and then we look at the eigenvectors. Eigenvectors will have information about communities. At last, I will talk about an open problem where we use spectral seriation for recovering the communities. So in general, communities capture underlying structure in the network. They reveal some functional information about the groupings in the network. And they help us to simplify and interpret complex networks. So this diagram is from the book by M.J. Newman. There are various books and the co-purchase of the books correspond to an edge between the books. So the nodes are the books. They belong to various categories like liberal, conservative, etc. So people use various models of random graphs to understand real world networks. So we create a model and we look at the community structure in the model and we look at the algorithms for recovering the communities in the model. So one of them is stochastic block model where we have probability P of some P in, probability of having an edge between the nodes of different community. So then we have conditions on P in and P out and on the number of nodes. Then we look at various algorithms that can recover the communities given the adjacency matrix of the model. So one popular algorithm is recovering communities using the Fiedler vector of the Laplacian. So we have this model, we have the graph, we construct the Laplacian of the graph. Then we look at the second smallest eigenvector, second smallest eigenvalue, and the corresponding eigenvector is known as Fiedler vector. If the Fiedler vector sign is positive, we assign that particular node to one community. If the Fiedler vector sign is negative, we assign that particular node to the second community. So this is known as spectral clustering via Fiedler vector sign. So this kind of clustering minimizes some geometric cut between the two clusters. Yeah. So given a graph, I have the adjacency matrix A with entry Aij equal to 1 if node I and j are connected, Aij is 0 if they are not connected. This is the adjacency matrix of the graph. Then I will have a diagonal matrix known as D, where each diagonal entry corresponds to the degree of the node. Okay, so if first node is connected to, let's say, k other nodes, then D11 is k. Okay, so this is known as Laplacian of the graph. So diagonal entry of D is sum of the row entries of A. So all one vector, so if I have all one vector, if I multiply all one vector to this Laplacian, sorry, that will give me 0 because diagonal entry is nothing but the sum of the row entries. So all one vector is the smallest eigenvector corresponding to smallest eigenvalue, that is 0. The next eigenvalue is known as Fiedler value. Okay. So lambda 1 is 0, lambda 2 is Fiedler value. If a graph is connected, it is non-zero. If graph is disconnected, we can show that lambda 2 is also 0. So yeah, corresponding vector is Fiedler vector. So I'll write U2. So given a graph, I don't originally know which vertex belong to which community. So adjacency matrix is a matrix like this. I have V1, V2, V3, etc. Vn. Similarly, V1, V2, etc. Vn. So these are the different vertices they correspond to adjacency matrix. So now I have a vector U, which is Fiedler vector. It has entries inside it. So let's say 1, minus 1, 2, minus 3, 4, etc. So now this one correspond to V1. So I'll assign V1, V3, V4, etc. to one community. V2, so V1, V3, V5 to one community, V2, V4, etc. to one community. So this is the traditional spectral method which minimizes the cut between the two communities. Yeah, we need lambda 2 to be non-zero. If lambda 2 is 0, there are two connected components. So, yeah. Yeah, if they are disconnected, then definitely we can have connected components belonging to the different community. But the interesting scenario is when there is connection between the communities. That is the challenging part. Yes. Yeah, so I will explain it now. So suppose I have k communities in stochastic block model. Okay, so then it turns out I have lambda 1, which is 0. Lambda 2 has multiplicity k minus 1. Okay, so lambda 2 as an eigenvalue, it has multiplicity k minus 1. In the expected matrix. Okay, but in the random model, lambda 2 may be, there are many k minus 1 eigenvalues near to each other. Space, every row is a node. So now V1 correspond to the first row, V2 correspond to second row, etc. So in SBM, we can apply k-means clustering on this k minus 1 dimensional space with k clusters. We can apply k-means clustering and it will recover the communities. So that depends on the parameters. So how P in and P out are related with n. So do they vary as 1 by n, do they vary as log n by n, or are they constant? So this is stochastic block model and spectral method for recovering the communities. So next we go to random geometric graphs. So stochastic block model is an extension of Erdos-Rini graph, which has probability p of having an edge between any two vertices. Random geometric graph, brings geometry into picture. So the nodes are in some metric space. Nodes are connected if they are within certain distance. If they are far away, then they are not connected. So this is a random geometric graph. So random geometric graph is important because people model wireless sensor networks and multi-agent systems and robotic visibility communication graphs, etc., using random geometric graphs. So in one dimension, these random geometric graphs are interval graphs. So we can take two intervals, multiple intervals. If the intervals overlap, then there is an edge between those two vertices. So extension of random geometric graph to multiple communities is geometric block model. So this geometric block model was introduced by Galhotra, Majumdar, Pal and Saha. So in 2018. So we have, so in geometric block model we have so two nodes are of the same community and they are connected. And if they are a different community, they are connected only if they are nearby. If they are far, they are not connected. So that's the inter-community radius. So this is known as R in, this is R out. If they are within R out, then they are connected. So if they are within R out, then they are of any community, they are connected. If they are within R in and they are of the same community, then they are connected. So random geometric block model also has various regimes in which we can study them, where R in and R out depends like order of 1 by n, order of log n by n, or they are constant. So yes, points are IID uniform in the metric space we are considering. So this is an example of, this is an adjacency matrix of geometric block model on a circle. So on a circle, yeah, so I will take, for this particular case, I have a circle, unit circle, and I generate uniform random points on the unit circle. Yes, yeah, on the circle, circumference of the circle. First I generate n points. Now I will uniformly assign one of the community label. Yeah, so there are n points and our study is n tending to infinity. Radius 1. Yeah. Yes, yes, more and more points. And now the radius, yeah, that's why we have connectivity radius. So if, yeah, that will go down. So I will assign the community labels uniformly from 1 to k. So 1, 3 or k, etc. So uniformly, and then connect them depending on the distance between them. So this is on a circle. So we can see the nodes nearby are connected and nodes far away are not connected. So, and there is some edge effect because of the circular thing. And this is when I sort the vertices according to their position on the circle. In general, I don't know this, I don't know their position, I only have the information of the adjacency matrix.
So here you're not showing classes though, right? You just do the same.
Yes, yes, yeah, it's just the connectivity, it's not classes. So when Galhotra, Majumdar and Saha introduced geometric block model, they took some real world networks and then they showed that geometry appears in real world networks. So some effect of geometry appears. So we can't really say what type of geometry, but so they showed that motif counting, the algorithm which they introduced, performs better than spectral clustering on these graphs which have some geometric influence in them. So here they have motif counting, accuracy and runtime, etc. So motif counting is basically counting the number of triangles supported by an edge. So I have two vertices. If they are of same community, then the assumption is there are more number of triangles supported on that edge. If they are of different community, then there are less number of triangles supported on that edge. So this is motif counting algorithm, and here they have T1, T2, T3, which are some parameters which they compute for that algorithm, and their condition is when A is greater than 2b, in Rn is A log n by n, R out is B log n by n. When A is greater than 2b, the motif counting performs well on this geometric block model. Yes, even if A and B are very small and A is greater than 2b, it performs well.
But then you are not in the connectivity regime.
Yeah, so yes, so okay. Yeah, here log n by n is something that is going to 0, but we don't typically take A and B are going to 0. A and B are small constants. Yeah, and more number of points.
What's your connectivity threshold? Some eigenvalue of log n.
Yes, I think it's yes. Yeah. Yeah, the core question is, will the spectral method work on geometric block model? Spectral method performs excellent in stochastic block models. So this is the paper by, this is a result in a paper by Konstantin Avrachenko, Maximilian and Andre. So they showed that there is some eigenvector which is not the topmost or the fielder vector, which will recover the communities. So here in this figure we can see that there is some eigenvector which is corresponding to the seventh, let's say the seventh eigenvector. It is completely able to recover the communities, but remaining eigenvectors are failing. So remaining eigenvectors have accuracy 0.5. That means they're as well as randomly classifying the nodes. So yeah, here there are only two communities. Yeah, so this paper motivated me to do postdoc with Kostya, so I wrote him several emails and joined his group. Yeah, this is the algorithm. So we have inter mu in and mu out. They are the edge densities of nodes in the same community and node with other community. So we look at the eigenvalue which is close to mu in minus mu out by 2 times n, and the corresponding eigenvector is the one which is able to recover the communities. So they are the average intercommunity and intracommunity edge density of a vertex. Yeah. Yes.
Are mu in and mu out given to you, or do you estimate them from the adjacency matrix?
Yeah. So by looking at an empirical adjacency matrix, we can. Yeah, it's not possible to. Yeah, they are given to us. Mu in and mu out are given to us. Yeah. Because without knowing the communities, we cannot really compute mu in and mu out. Yeah. So this is our work. We extended this for k communities. So in k community case, we have k communities, equal number of nodes in each community, n by k number of nodes in each community, and the radius are uniform. Let's say R in is the intercommunity radius, and R out is R in is intracommunity radius, R out is intercommunity radius. So this is a result. We showed that there is some eigenspace, and in that eigenspace we can apply k means clustering to recover the communities. So this is a random geometric graph with 4 communities on a circle, and when we look at the eigenspace, those circles split into 4 parts, something like that. Okay, so that's some eigenspace. So next I will go into the proof, how we went about proving this particular thing. The core idea of the proof is by a mathematician known as Bordenave. He was looking at Euclidean random graphs. So in the 2 community case, they adopted it for geometric block model. In the k community case, we had to look at the for the spectral density, empirical spectral density, we had to do some new combinatorics, and for the eigenspace we had to go for like Davis-Kahan theorem, perturbation theorem of the eigenspace of the random matrix with the expected matrix. So these are the main challenges. So we assume our metric space is d-dimensional flat torus. So when d equal to 2, it's just a square, and it is flat torus. That means I identify this edge with this, and let's say this edge with the other one. So if I roll it, it becomes a torus. The vertices are mapped from 1 to n. Vertices have a map of community labels, and the positions are IID uniform on this d-dimensional flat torus. The edges have probability. Probability of Aij equal to 1 is from a function f of xi minus xj sigma I sigma j. So it depends on the distance between the nodes as well as the community labels. In the homogeneous case, the function is fixed. So if two nodes are of same community, the function is f in. If they are of different community, function is f out. So mu in and mu out are the edge densities of the intra-community and inter-community. So they are the integration of these functions over the flat torus. So expected degree of a vertex is n by k times mu in, because there are n by k vertices of the same community, and k minus 1 times n by k vertices are of different community, so it is multiplied with mu out. So first we look at the eigenvalues, and we look at the eigenvalue of an interest, that is mu in minus mu out times n by k, and we show that this eigenvalue is sufficiently separated from other eigenvalues. In the second step, we look at the eigenvectors.
Make no assumptions about the shape of Fn and F. I mean, there can be. You make no assumption about the shape of these connectivity.
Yeah. So there are assumptions which we use Fourier series decomposition. So they have to have a valid Fourier series decomposition on this flat torus. Yeah, but they will go to 0 after.
But there's no. I mean, one doesn't have to dominate the other everywhere. There could be holes in there.
Yes.
They could be.
Yes.
weird in all
Yeah.
sorts of ways.
Yes.
Yeah.
There. Yeah, but I haven't done any simulation on those things. I will try to. Thank you. So for looking at eigenvalues, we use movement method, where we start with a empirical spectral measure. Empirical spectral measure means whenever there is an eigenvalue, I will have a delta function at that position. So I look at the matrix A by n. Eigenvalues of a matrix A by n are lambda j by n. Okay, so I will have a delta function at that particular position, and mu n is sum of these delta functions, so that the integral is 1. So our goal is to show that this empirical spectral has a limit. So mu n tend to mu asymptotically almost surely. To show this, first we show that expected mu n tend to mu for all moments, that is Pm, which is some polynomial t power m. So next we show that this mu n, actual mu n, is very close to the expected mu n, and that goes to 0 almost surely. So then we have the proof that mu n goes to mu almost surely. Yeah, Pm is just a arbitrary, it's a notation for t power m. Yeah. So Pm of t is t power m.
So you show mu n converges to mu weakly by showing convergence of
Yes. Yeah. So mu n of Pm is 1 by n power m trace of a power m. So mu n of Pm is just the integral of t power n with mu n. So it turns out it is 1 by n power m and summation of eigenvalues lambda I power m. So that is trace of a power m. So trace of a power m has the interpretation that is number of closed walks of length m, which start at a vertex and end at the same vertex, and sum of all those walks. So next we would like to, so A is a adjacency matrix, but we would like to go to the functions, the probability f in and f out. For that we use the conditional nested conditional expectation trick. So that is expectation of something is expectation of A given x. So here the positions are x. So when the positions are given, the f are independent, so I will have the product in the expectation. So it is sum and integral followed by product of functions f of xi, xil minus xil plus 1. So they are indices. So this integration is over the product of these many terms in the, so this integration in the product of d-dimensional torus m times, because I am looking at a power m and thereof length m walks. So this integral is nothing but the convolution evaluated at 0, so convolution of those functions, and depending on the same community or different community, we have convolution of f in so many times and f out appearing some other times. Because this is convolution, we use the Fourier transform trick. So convolution is product of Fourier transform. So moments depend on f in and f out hat. So they are the Fourier coefficients. So this is the limiting measure we get. So limiting measure is sum over integers over d dimension. It's delta on f in hat of z plus k minus 1 times f out hat of z by k plus k minus 1 multiplied with delta f in hat of z minus f out hat of z by k. So actually when we do the computation, we get this term plus some other term which goes to 0 as n tending to infinity. So here note that we have k minus 1 multiplied with delta f in hat of z minus f out hat of z by k. So when that z is 0, that f in hat of 0 minus f out hat of 0 by k, so that's the dominant thing, and all the remaining terms they go to 0. So this is what we show, except delta f in hat of 0 plus k minus 1 times f out hat of 0 by k. So because of geometric effect, so there will be non-zero finitely many eigenvalues. So this is expectation of mu n going to mu, but we have to show the concentration around the mean, that mu n is concentrated around the mean. For that, we employ the Talleyrand inequality, and we get the exponential bound on deviation between mu n and its expectation. So, in order to apply Talleyrand inequality, so Talleyrand inequality says I have a product of spaces and I have some function evaluated on this product space. Then if that function is Lipschitz, we can have the concentration about the mean of that particular function. So, in order to show that it's Lipschitz, we compute the Lipschitz constant by changing just one particular vertex. How does the trace of a power m changes? So, next, because of the exponential control, we can apply Borel-Cantelli lemma to show the convergence, almost sure convergence. So, this is the spectral measure. So, what we actually show is, if you look at the limiting spectral density, there are, so one of the largest eigenvalue, that is f in hat of 0 plus k minus 1 times f out hat of 0 by k. So, that is the largest one, that correspond to difference. So, this correspond to mu in minus mu out by k times n. So, then there are some other eigenvalues and many eigenvalues near 0. So, this is the limiting spectral density depending on the functions f in and f out. And this distance, we also need to show that there is some epsilon distance which is positive. There are around mu in minus mu out by k times n. So, in that region there are no other eigenvalues. So, that is required for Davis-Kahan theorem. Yeah. So, next we go to the eigenvectors. So, we define a deterministic matrix which is kind of an expected matrix of A, expected matrix of the random model given the community labels. So, this B sigma of ij is expected A given sigma. Sigma is community labels. So, for example, in 4 communities, I have J which is all one matrix of size n by 4, and J is multiplied with mu in and mu out for 3 times. So, this is the structure of this particular deterministic matrix, where J is the all one matrix of size n by 4. So, this is a deterministic matrix and it has corresponding eigenvalues and eigenvectors. Our aim is to show that eigenvectors of A, that eigen subspace of A corresponding to mu in minus mu out by k, can be rotated, and it can be rotated in such a way that it is very close to the subspace of this particular matrix B. So, we use some kind of perturbation of B and A. So, eigenvalues of B are, yeah, there is no need. So, we, yeah.
I mean, this sort of makes the analysis
So,
clear.
yes, that will make it very interesting. Yeah. So, maybe there are multiple eigenvalues in this. There are k minus eigenvalues. They have the same subspace, but they will be nearby each other. The k minus 1 eigenvalues will be near each other. So if I look at the eigenvectors of this particular matrix B, it has, I can choose the basis in such a way that the first eigenvector is all 1, and the eigenvectors, 3 eigenvectors corresponding to the 4 communities can be 1 minus 1, 0 0, 1 0 minus 1 0, 1 0 0 minus 1. Note that there was J matrix, so this 1 will be repeated n by k times, minus 1 will be repeated n by k times, 0 will be repeated n by k times, etc. So they are k minus 1 vectors, they span a k minus 1 dimensional subspace. Now we have to control the eigenvectors of A. So in order to do that, we will compute the partial sums of the entries. So this ypq of I is sum of, so first let's say we arrange A with in blocks corresponding to the communities. So I have block 1, block 2, block 3, etc. So in this particular block, I will just compute the sum of the entries in a particular row that I am calling as ypq of I. So I am doing this because I want to show that that sum is, so I have taken motivation from this eigenvector structure. That is, the same entries are repeated n times. So this sum is one of the entry of the eigenvector. I mean, the sum of these sums is one of the entry. So there are k minus 1, these terms, sorry, k times k of these terms, they will be added to give one entry of the eigenvector. So it is an average of ypq of I is an average of independent Bernoulli random variables. So we can apply Chernoff bound to show that they are very close to their expected value. So now we use a Davis-Kahan theorem. So in Davis-Kahan theorem, it says that if a matrix A is perturbed into matrix B, then if there is any eigenvalue lambda and it has some spectral gap, that means there is no other eigenvalue nearby, then the corresponding eigenspaces can be rotated in such a way that the difference between them can be made, can have an upper bound. So this is VQ minus U Frobenius norm. Here U is the eigenvectors of the matrix, deterministic matrix B, and V is the eigenvectors of random matrix A. Then Davis-Kahan says that there is some rotation matrix, orthogonal matrix, such that VQ minus U Frobenius norm can be bounded by some constant times A minus B sigma times U Frobenius norm divided by epsilon n, where epsilon is the gap, spectral gap, so that there is no other eigenvalue lying closer than epsilon. So we have this A minus B sigma times U. So this A minus B sigma times U can be written in terms of those yi, which is these yi's, the sum of the entries of A along a particular row. So then we can apply a union bound to get order of root log n with high probability. So now when we substitute these things in the Davis-Kahan theorem, there is n there in the denominator and root n log n. So we'll get root log n by n, so under the whole root, which goes to 0 as n tending to infinity and with high probability. So therefore, the eigenvectors of A are eigenvectors of A divide the vertices into communities in that particular subspace. So we get a structure like this, that I showed before. So we have, this is the eigenspace, 3-dimensional space, and they are the vertices. So we can apply k-means clustering algorithm to recover the communities. So for that to work nicely, we need to have certain bounds on R in and R out. They have to be, R in has to be sufficiently larger than R out. So weak consistency is nothing but the fraction of error is going to 0. That's weak consistency. So now I'll go to the next part, which is in the log regime. So whatever we did till now is in the constant regime, constant R in R out regime, which is independent of n. So in the log regime, the spectral methods don't work for geometric block model. Or if I correctly phrase it, we don't know how to make use of the eigenspaces to recover the community structure. So we have adjacency matrix given in the log regime, and our aim is to find the community structure. So in log regime, the algorithm which works best right now is Galhotra-Mazumdar's motif counting algorithm. So in this experiment, I took one-dimensional geometric block model, and R in is a log n by n and R out is b log n by n. Motif counting says that when a is greater than 2b, we have recovery guarantee. So we looked at spectral seriation. Spectral seriation is a technique that is used for sorting the vertices of a graph, or it can also be used for sorting various things, for example data points which have some relation with each other. So originally people looked at spectral seriation for in archaeology. So they were in different timeline. So when people excavate a particular site, they will get different potteries, but they have to assign a timeline to each pottery. So some potteries we can, with high confidence, we can say, okay, this belong to a particular century, but others we may not able to say. So the idea is similar potteries belong to similar timeline. So in general, spectral seriation is sorting the vertices of a graph. Suppose in this, so let's say on a circle, I don't know the positions of vertices, and they are random. They will be, the adjacency matrix have non-zero entries in random fashion. But if I know the order, I can have that banded pattern. So something like this particular band, and there is some edge effect due to the circle. So given a matrix in this form, spectral seriation will find a permutation P such that P, the particular matrix P transpose, is of this form, which has the positions recovered. So spectral seriation minimizes the bandwidth of, so basically we have to be in one dimension to sort the vertices. So so I will explain that later. So now, so in one dimension, if I permute, I find a narrow band. So the permutation is using the Fiedler vector entries of the Laplacian of that particular graph. So I have the Fiedler vector just as before, 1, -1, 2, -3, 4, etc. Now I will sort the vertices. The vertex with -3, so this is V1, V2, V3, V4. So V4 will come first, then V2, then V1, then V3. So this is how I permute. By looking at the eigenvector entries, I sort the vertices. So after sorting the vertices, the claim is bandwidth is minimized. So once the bandwidth is minimized, this is the part where I don't have a rigorous proof. So we can show that spectral seriation recovers the order for certain type of matrices, but this geometric block model is not among those classes, not among the known matrix classes. Yeah. So now suppose given the position is correctly recovered, I know the graph structure. So within certain distance, they are all connected. So I'll start with a particular row. For example, I will take row 2, and within certain distance, they are connected. So the vertex 1 is connected, vertex 3 is connected. But after certain distance, there is some 0 appears, let's say. And that means that is a node 4 and 2 are of different community. So they are not connected, and the node 4 and 2 are away from R out. So anybody who is connected after that node 4 is of the same community as node 2. So I call this algorithm as first 0 R out algorithm. That means wherever first 0 appears, that correspond to R out. Whoever after that first 0 is connected to me, they belong to the same community as mine. So now we recursively recover the community labels. So now 2 and 5 are connected. Now I will go to the row 5, and there may be some other vertex which is connected. So experimentally, I saw that this particular method recovers community when a minus b is greater than 2. So here a values and b values, whenever they are greater than 2, there is complete recovery. It's 100% able to recover. Yeah. So now that is for geometric block model on a line. If it is on the circle, I can remove the neighbors of a particular vertex, one particular vertex, and then it will become a line, topologically equivalent to a line. So on that line, I can do the first 0 R out algorithm. Or if I look at the eigenspace of the first 2 Fiedler vectors, the nodes are embedded in a circle. So here the geometry is coming into picture. It's not recovering the communities. If I look at the first 2 Fiedler vectors, first 2 vectors of the Laplacian, the vertices are overlapped. The two different community vertices are overlapped on each other. So there is geometry coming into picture. So the effect of geometry is preventing us from getting effective algorithm for community recovery. Yeah, so then again we can do first 0 R out algorithm on the matrix we get. Yeah, so yeah, I'll stop here. Okay. Thank you very much. Yeah.
Thank you, Professor, for accepting the request and delivering an interesting talk.
Thank you.
Are there more questions
Yeah.
from the audience?
Okay,
So
this
in
part
the logarithmic case, it's
is
still a conjecture.
is still a conjecture. Yeah. So it recovers the community, it recovers the latent order is the part which has to be proved. Okay. Yeah. So when they looked at the distribution of the triangles, so when they looked at the distribution of triangles, so it has to. So they computed these T1, T2, T3 quantities. Okay. So based on that, they will do the thresholding, and all these T1, T2, T3 quantities. Okay. Yeah. So these T1, T2, T3 quantities, they're like they compute several things. So one is how many nodes can fall between, so they compute in the geometric space, how many nodes fall between that particular radius. So I have V1 and V2, how many nodes fall within that radius, and how it is related to Rin and R out, etc. So based on that, they compute T1, T2 and T3 in the limit it corresponds to A greater than 2B condition. So it's,
I mean, even for a circle, you can actually do this triangle thing, right? That
yes, we can do thing, but in circle it works for A greater than 2B cases, but not for A minus B greater than 2.
Just to remind myself of the model. So you have a connection function that depends on the distance.
Yes.
And Rin is the mean of this connection function. Rin and R out are the means.
Yeah.
of
So
the
yeah. So there are, yes. So I'll explain it. So in this particular case, this is geometric block model. Okay. So in this geometric block model, that connection function is something like this. So f in at 0 till R in, it's 1 and it's 0 everywhere else. F in is this. F out is this.
I mean, it's just an indicator, right?
Yes, yes, indicator that less than, yeah, between 0 and R in, between 0 and R out. Yes, this is R out.
Is this an
But-
is this an example, or is this the only F in and F out that you consider?
No. So this is an example in which we compute and do the experiments. But the proof is general for any F in and F out.
As long as the area. And
Yeah,
the
as long
area
as
is
the area is mu in and mu out. Yes. So this is geometric block model. This is a special case of that soft geometric block model.
Thank you again, Professor. Thanks
Thank you.
everyone for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there.
Thank you.